So in this video we're going to look at the sequence of prime numbers and the sieve of Eratosthenes. So the sequence of prime numbers you've probably seen before at some point. It starts with the smallest prime, which is 2, 3, 5, 7, 11, 13, 17, 19, just write out the first few primes up to, say, I'll just follow Hardy and Wright. So they go up to 53. So we'll stop there. 47, 53. So these are all prime numbers arranged in ascending order. How might we extend this list, or how might we even arrive at this list? Obviously, people have already thought about this stuff before, so you can just look it up and you'll be able to find a table of prime numbers. But how would you construct one for yourself? Well, you could use this sort of the brute force approach by just starting at 2 and then say, well, is 2 a prime number? Yes, it is. Okay, add it to the list. Then you move to 3. Is 3 a prime number? Yes, it is. Add it to the list. Then you go to 4. Is 4 a prime number? No, it's divisible by 2. Don't add it to the list, etc. 5's on the list. 6 is not. 7's on the list. 8's not, and so on. So you could go through every number systematically and brute force it. Now that's one way of doing it. A better way of doing it would be what's called the sieve of Eratosthenes. So here you can see a grid of numbers from 1 to 100. So we'll demonstrate the idea behind the sieve of Eratosthenes using this grid. So we start by taking the multiples of the first prime number and deleting them from the grid. So we're not going to look for every prime number, we're just going to look for the prime numbers up to some arbitrary limit, in this case 100, to demonstrate how it works. So if you've got a finite endpoint, then you can use this method. And obviously the more numbers you use, the bigger the set of numbers you use, the longer it will take to use this. The more numbers you have, the longer this method will take, but as long as you don't have an endless list of integers like we actually in fact have, then this method will work just fine. So first of all, so we're going to look for all the multiples of 2. So we'll leave 2 alone, but we'll scrub out 4 and 6 and all the other even numbers, so on and so on. So skip ahead here. So you can see that all the even numbers appear here in these columns. So get rid of those, and 2 is still there because it's prime. 1 obviously, 1 isn't a prime number, so we'll exclude that from the beginning. The next number is 3, so we're going to pick a different colour, and we're going to delete all the multiples of 3 from the grid. We'll leave 3 obviously, so 6 is already gone. Going to want to erase 9, 12's already gone, 15, and so on and so on. So just skip ahead. Let's see the multiples of 3 erased here. Some of them are already deleted, i.e. the even multiples of 3 are already erased or hidden in red. Next of all we have 4, but we don't need to look at 4 because all the multiples of 2 include all the multiples of 4. So in fact we only really need to look at the prime, the small prime numbers. So 4 isn't prime, so we'll skip to 5. We want to leave 5 there because it's a prime number. All the tens column here, they're all by virtue of being even numbers, they're all not prime already, so we can just worry about the every multiple of 5 is either ends in a 5 or ends in a 0. So 5's gone, 15's gone, 25. Oops, let's change colour. So all of these ones that hadn't already been coloured in, they'll go now. And then we'll move on to 7, multiples of 7. Again, a different colour this time. We'll leave 7, 14's already gone. Most of these are already gone, in fact, so the only ones we haven't already got 49, 77, and 91, I believe. And the next prime number after 7 is 11, which is in fact greater than the square root of the highest number on the grid. So that, I haven't mentioned up until now, but that is the condition at where you stop. Okay, so the reason this works is, if we had, say we had big N numbers on the grid, and we were interested in the number little n, which was less than or equal to the big N, provided we know that n is not prime, i.e. it has divisors other than itself in 1. One of those divisors, let's call it p. So p is a divisor of n. If we know that p is a divisor of n and the n is less than or equal to big N, then that must mean that p is not greater than the square root of big N. So if p divides n, then p can't be greater than the square root of n, i.e. we only have to check up to the square root of the biggest number. So for instance, in this example where we counted up to 100 on the grid before we started using the Sieve method, the square root of 100 is 10, so we only need to consider primes which do not exceed 10. So as soon as we get to 11, we're done. Don't even need to start bothering with multiples of 11. If we had extended this grid up to 150, then we would have stopped at 13, because 13 squared is 169, which is greater than 150. But on our 150, or a grid with 150 numbers, we would have had to have served out all multiples of 11, and that's why it's called the Sieve, and it's named after Eratosthenes, who is credited with this method. So that's basically how you construct a table of prime numbers more efficiently than brute force. Now, the prime numbers form a very interesting sequence which fascinates number theorists, and indeed almost all the number theory is purposed towards understanding why the prime sequence is the way it is, what properties it has, what properties can we learn about it, how can we understand the sequence through constructing analogous systems that extend the integers, like Gaussian integers or other forms of analogous systems that might teach us about the integers. So yeah, that's where this road goes. But the Sieve of Eratosthenes is the most simple and straightforward Sieve method. There are others. There are many more advanced Sieve methods in number theory, but this is really the easiest and first one you should look at.